All right, welcome to day 2 of review 1 from last year. We'll be looking at inverses, piecewise functions, and modeling today. Now our warm-up, we're just going to talk through this warm-up together. It's something that we'll do. This is an example of a piecewise function, one of the ones that we'll see today. So a piecewise function is basically different pieces of functions depending on which x values you use. So the meaning of this is when x is greater than or equal to -2, you should use the top equation. But if x is less than -2, you should use the bottom equation. So say you wanted to do like f of -4. Well, this means we should sub -4 in for x, but which equation do we use? Well, -4 is less than -2, so we should use the bottom equation. So we do -3 times -4 plus 1. That would give us 12 plus 1, or in other words, 13. If we had something like f of 0, well, 0 is greater than or equal to -2, so we should use the top one. So we do 2 times 0 plus 2, which is 0 plus 2, so you get 2. So piecewise function is just different functions depending on which x value you use, so you have to decide which one you should use depending on the x value that is given. And we'll see those today. If we go over to the homework, we're given 2 points. Got to do y2 minus y1 over x2 minus x1 to get the slope, and we get 5, 6. Then put that into our y equals mx plus b. The 5, 6 is m. Then I chose to use 5, 2. You can use either point. I put the 5 in for x, 2 in for y. Multiply, subtract over. You get b is negative 13, 6. And then write the equation of the line, filling in your m and your b. In 2a, start out put negative 11 in for x and g's equation, you get back negative 6. Then put that into the f equation, and you get negative 1/3, because when you have a composition, you work right to left. Compositions can be shown with the open circle or the double set of parentheses like we have in b. So in b, we do the inside first, f of 4. So put 4 in for x in the f function, we get a half back. And then put a half in for x in the g function, and we get 5.5. Or you could have also called that 11 halves. And then algebraically, g of x is on the inside, so we're going to put g of x's entire expression in for x in the f equation. So you have 2 over x plus 5. And then we're reverse in d, so we'll put f of x is 2 over x in for x in the g equation. So 2 over x plus 5. For your graphs here, you had to extend in number 4 a bit for it to fit, or you had to raise your x-axis some, one of those two. But you can put these in, do a control T to get your table and get some actual points. So we had each of those graphs, then we wanted to tell the domain and range. Well, in the left-hand one, our leftmost x value is -2, and then we go forever to the right, so x is greater than or equal to -2. And for y values, our lowest y value is 0, and then we go up forever, y is greater than or equal to 0. In the right-hand one, we go forever left and forever right, so domain is all real numbers. And the range, the lowest we go is -17, then we go up forever, so y is greater than or equal to -17. All right, we're going to be on page 8 in our Unit 1 from last year review packets. And we're going to start out with inverses. So when you have two inverse functions, any point in the original just gets reversed. So what I mean by that is if 2, 3 is in the original, in the inverse it becomes 3, 2. So they just get reversed. So a lot of times actually on the Regents exam, if it's a multiple choice, you can just graph the original, do a control T and pick out 2 points, then graph each of the choices and do a control T and just see which one has those 2 original points reversed. So if it's not a multiple choice though, we need to be able to find the equation. That's what we're going to practice today. Now graphically what's really happening is it's reflected over the line y equals x, and that's why the x and y values are just exchanged. This little -1 here, that's the notation for inverse. Okay, that is read as f inverse of x. And we're going to think of this as y for us to find the inverse. Well, an inverse is the x and y switch. So we're literally only going to change the x and the y. So this becomes x equals 2y minus 5. And then we'll work to get y alone. We'll add the 5 over, giving us x plus 5 equals 2y. And we'll divide by 2. So we could either have that y is equal to x plus 5 all over 2, or you could have also written them individually over 2 and written 1/2 x plus 5/2. Either of those would be considered correct. All right, next one, we want to find the inverse again. We know that by our notation. So we'll write this as y equals square root of x plus 4 over 3. And we'll change our x and y. And only the x and y get switched. Everything else stays exactly where it is. We can put the x over 1, and we can cross multiply. So this will give us 3x equals square root of y plus 4. To undo the square root, we will square both sides. 3x times 3x gives us 9x squared. And on the right, the square and the square root wipe out. And to finish getting y by itself, we just got to subtract the 4 over. So our final answer, we've got f inverse of x is equal to 9x squared minus 4. All right, we're going to find the inverse of this function. So here's our original, y equals that. And we will switch where the x and the y are. Now let's work to get y by itself. So we'll subtract the 7 over. We'll divide everything by 2. And then the opposite of squaring something would be the square root. So the opposite of cubing something would be the cubed root. When you do odd roots, you do not need a plus and minus out front. Only when you do even roots. So like square roots and fourth roots. So that is our inverse. So our notation we would write f inverse of x equals the cubed root, and all underneath x minus 7 over 2. All right, we're going to do 2 more inverse examples, and these, notice, are really similar. The difference is the top one has the plus 8 outside of the cubed root, and the second one has the plus 8 inside the cubed root. And we're going to see how do those look differently when you go to get the inverse. So we'll start out, we'll change our x and our y. Well, we always undo any outside addition and subtraction first. So this 8 is going to get subtracted over first. Then we got to undo any multiplication or division, so we'll divide by 4. And then the opposite of cube rooting something would be cubing it. So we're going to raise both sides to the third. So our final answer, we would have f inverse, or oops, we don't have f here, we actually have h. H inverse of x is x minus 8 over 4 all cubed. Well, let's see what the difference is now when the plus 8 is on the inside. So our original, we'll just write that with our y to start out. we'll switch the x and the y. And in this case, there wasn't any addition and subtraction on the outside, so we do the divide by 4 first. Our next thing that needs to get undone now is the cubed roots. So we'll raise both sides to the third. So I'm going to come up here. So that'll give us x over 4 equals, the cubed and the cubed root wipe each other out, so we just have y plus 8. Subtract 8 from both sides. And again, we had h, so our inverse notation, we'd have h inverse is equal to x over 4 all cubed minus 8. So notice a slight difference in the original equation yields different inverses, different order that things need to be undone. All right, so that's it for our first topic, inverses. Now we're going to look at piecewise functions. And I'd like you to, in your tables, I'm not sure if I did it already, but cross out the 1.1 and the 4.9. We're not going to be having things in those spots. All right, if x is less than or equal to 1, that's our left-hand table. So at 1, because it's got an equal to, we would need a closed circle. So I like to write a closed circle next to that to remind me. And then we have values that are less than 1, 0, -1, -2, -3. Well, we could have kept going. So because we could have kept going, I like to put an arrow there to remind me that when I graph this, I need to stick an arrow on the end. Now in the other one, we go from 1 to 5 and we don't have an equal to. When you don't have an equal to at those values, you get an open circle. The open circle signifies that point is not actually included, but you can get as infinitely close to that point as possible. Now, we don't go forever past those. We only go 1 to 5, so we don't have any arrows. All the other points, we'll plot just regular points. There's nothing fancy about them. So you can do this one of two ways. You could sub in by hand, or you could do x plus 2 in a graphs page and do a control T and just get the y values that go with it. We'll just sub them in by hand here. -3 plus 2 gives us -1. -2 plus 2 is 0. -1 plus 2 is 1. 0 plus 2 is 2. And 1 plus 2 is 3. In the other one, we're just negating x. This is -1, -2, -3, -4, and -5. So in the first table, I'm actually going to plot the bottom one first. So we have 1, 3 with a closed circle. Then we've got 0, 2, -1, 1, -2, 0, -3, -1, and we need to have an arrow then. So that is our graph for the first part. For the second part, we start out with 1, -1 with an open circle. So that would be here. Then we have 2, -2, 3, -3, 4, -4, and at 5, -5, we also need an open circle. And you just connect the edges of the open circles when you draw that. And that's it for our graph of our piecewise function. If we go to the next page, we're going to try another one. So for this one, we're going to need 4 t-tables. So for the first one, we want x to be less than -2. So let's start with -2 and put an open circle next to that because we don't have an equal to. That we want things less than -2. So like -3, -4, and we could keep going. So since we can keep going, let's put an arrow, and that'll remind us to put an arrow on the graph there. In the second one down, we go from -2 to 2. At -2, we have an equal to, so we want a closed circle. And then we've got -1, 0, 1, 2. At 2, we don't have an equal to, so we'll have an open circle. And again, all the other points are just regular points. The next one, we only have a single value. At x equals 2, they tell us that it's -3. So that's just going to be a regular point, because it's got an equal to, and that's all we'll have for that one. And then the last one, we have x is greater than 2. So we'll start at 2 with an open circle. And then things greater than 2 are like 3, 4, and we could keep going, so we'll put an arrow there. So you could either put those each in a graphs page and do a Control T to get the y values, or you could just do them by hand. So if we started by putting -2 in the top one, 4 minus a -2 is really 4 plus 2, so that's 6. 4 minus a -3 is really 4 plus 3, so that's 7. 4 minus a -4 is really 4 plus 4, that's 8. In the second one, -2 times -2 is 4, then plus 2 will give us 6. -1 times -1 is 1, plus 2 will give us 3. 0 times 0 is 0, plus 2 gives us 2. 1 squared is 1, plus 2 is 3. 2 squared is 4, plus 2 is 6. The third one we're done because we just had a single point. And notice in the last one, they're saying it's just always 6. So these are just all 6s. So we can plot this now. So -2, 6 with an open circle. And then we have -3, 7, -4, 8. And we'll have an arrow on that. The next one, -2, 6 is a closed circle. Well, notice that's right where the open circle is. If that ever happens, all you do now is just fill in the open circle. Then we have -1, 3, 0, 2, 1, 3, and then an open at 2, 6. Now this was an x squared. X squared, oops, I went too high on that one. That should be there. An x squared should be a parabola. So this should have some roundedness to it, not a point. Next up is a single point at 2, -3. Then we have an open circle at 2, 6, which we already have. Then we've got 3, 6, 4, 6, and we've got to put an arrow. So it just ends up heading out to the right. And that's it for piecewise functions. So the rest of the video, we're going to work with the calculator. So make sure you have your calculator out and ready. So we have two functions. F of x is going to be the height of an arrow, or the path of an arrow, and g of x is the path of a bird. And we're going to graph both of them at the same time on a graphs page. So let's go over to the calculator, add a graphs page. And for f of x, we have -16 x squared plus 60x plus 5. Well, notice based on this right now, okay, a -16x squared, that should be a parabola opening upside down. We can't see the parabola part, so let's make it higher. We can double click that 6.67, and let's try like 50 maybe. Still not high enough, looks like we're getting closer. Let's maybe try like 75. All right, and that looks better. Now, if you don't want to just guess, what you always could have done is you could have done Control T and just scrolled through the table to see what some of the values are. So like we have a 61 there, so we know we would have had to see greater than 61. To get rid of the table, just do Control T again. So we want to graph our second function, the g of x. You can either do Control G or Tab to bring the graphing line back up. So that's 5x plus 20. So the blue is the arrow and the red is the bird. So let's go back to our packets on page 11 now. And we want to know what's an appropriate domain for these functions. Well, we're working with x's in seconds, and you can't have a negative number of seconds. So on the low end, we know that x should be greater than or equal to 0. The other thing we have to be concerned about is the blue one, the arrow, it can't really go below the ground. So really our scenario ends essentially when the arrow hits the ground. So let's find when that arrow hits the ground. On your calculator, we can go Menu, Analyze Graph, and 0. Select which graph you want. So I'm going to select the blue graph. It wants the lower bound, so pick something to the left of it. Upper bound, pick something to the right of it. And then that tells us we've got 3.83. Now, a feature I want to show you on the calculator is if you ever need to see more decimal points, click it once and hit the plus sign. Let's see. I know it works on yours. I don't know if it works on the smartboard. But click it once. Click the X value once. Maybe it's not going to work on the smartboard. Yeah, I guess it doesn't work on the smartboard. But on yours, if you click the X value once and hit the plus sign, it will show more decimal places. So our domain should go till 3.83. So if we go down to the bottom of page 11 now, go to Menu, Analyze Graph, Intersection, and find our intersection points, and then explain the context. So we're going to go to Menu, Analyze Graph, Intersection, and let's find that left intersection first. So go left of that intersection, right of that intersection, and we get 0.299 and 21.5. Now, keep in mind, if you want to find more, just click the X or Y value, whichever you want more decimal points of, and hit plus, and it'll show you some more. Well, let's find the other one. Menu, Analyze Graph, Intersection. We'll find the right-hand intersection. So that's left of it. Click right of it, and you got 3.14, 35.7. And what is this in the context? Well, remember the X was our seconds and the Y was the height. So it is when, so in other words, the X, and where, so the Y, the arrow and bird meet. So in other words, the arrow hits the bird. The next one, we want to know when is f of x greater than g of x? Well, notice that's in the middle, in between those intersection points. So you usually describe that in terms of x's, and they tell us right here for what values of x's. So we have 0.299. Notice we don't have an equal to, so we'll have less than x less than 3.14. And what's happening when f of x is greater than g of x? It is when the arrow is above the bird. All right, we're going to skip the bottom one on a left. Okay, so over on 12, we want to find the maximum point. So we want the maximum point of the parabola. So menu, analyze graph, and maximum. Which graph? We'll select the blue one. We've got the lower bound, the upper bound, and we get 1.87, comma 61.3. Okay, so again, those aren't the whole numbers. If you click and hit the plus sign, it'll show you more stuff. Well, what is this? Well, it's for the arrow. It is when the arrow is at its max height. And that's the x value. And it also tells the max height. And that's the y value. Well, we want to know for what values of x does f of x, so the parabola, increase. Well, it's increasing, so a positive slope everywhere left of that maximum point. So we have anywhere between 0 and the x value for that maximum point. Well, when does it decrease? Everywhere after the maximum point. So from 1.87, less than x, and we found that it hits the ground at 3.83 seconds back in the beginning. And then lastly, when does it hit the ground? Again, we found that as 3.83 seconds when we did our domain. Down on the bottom, last one for this video, what's the average rate of change? When you see average rate of change, we need to think slope. So we want to go from 1 to 3, and we're doing it for f of x. So we're going to have 1 comma something and 3 comma something. Let's go to our table by hitting Control T. And for f of x, 1 was 49 and 3 was 41. And now we'll just do a slope. So 49 minus 41, our y minus our y. Because we started with 49 on top, we got to start with 1 on the bottom. So we'll have 1 minus 3. That'll give us 8 over negative 2, or in other words, negative 4. And our units would be feet per second. It's a slope, so it should be something per something. And what that means, on average, the arrow was dropping 4 feet per second over that time interval. So from 1 second to 3 seconds, on average, its height was lowering at 4 feet per second. All right, that's it for this video. You got page 13 for homework.